So thank you to the organizers for inviting me, and thank you to you for coming. I was given the title actually by the chairman of this session, and I'm not a historian, I'm an active physicist in this field, but I'd like to draw, if not a precise historic account of what has quantum information developed like in Europe, I like to tell about some of the scientific roots that actually formed the community and how the community around quantum technologies was established in Europe. That is never a straight path. That's always different contributions that are being melted together, and I will share with you how I see that melting together, and also how the strategies for quantum technologies developed along with that in Europe. So let's just go all the way back to the ones in the room who are not quantum physicists. Quantum mechanics appeared more than 100 years ago, and as a Dane I have to show you, of course, Niels Bohr's model of the atom. Being in Lund, I also have to say that what Bohr really confirmed with this model of the atom was, of course, famous Lund scientist Rydberg's spectra observations from the atomic systems. So Bohr made this model of an atom where electrons are moving in particular orbits, and in these orbits they actually don't radiate, but they radiate when they jump between the orbits, the discrete state, energy states of the system. And Bohr made a formula, and that formula with 5-digit precision was actually in agreement with the hydrogen spectrum. And the formula was also already predicted by Rydberg from observations. If you go to other atoms, for example, helium, who has 2 electrons instead of 1, it's a really bad approach. It gives 15% disagreement, no matter how much Bohr was tweaking the parameters and tweaking his students into doing the calculations. And of course, as you know, if you're working quantum physics, Bohr's model of the atom is not right. It's actually a wrong model of the atom, but it was a stepping stone towards the quantum mechanics that appeared in the next decade, for example, with Schrödinger's wave mechanics. So here's the Schrödinger wave equation, which is just looking like actually any other wave equation. Sound wave equation, electromagnetic wave equations have similar structures, but the one he wrote down here contains the potential of the particle moving around. It contains the position coordinate, but it's no longer a classical particle. It's actually a wave which is everywhere in space. And when you solve for the wave functions, then you find, for example, for the hydrogen atom, number of different wave solutions. And I just couldn't resist showing you that the wave patterns you find in the atoms look like wave patterns in the macroscopic world. So this is a guitar playing a deep tone, and this is playing a high-pitched tone, and you see exactly this wave pattern in the Rydberg atom here. And it's, of course, a completely different story. I mean, you have to interpret what does this wave function mean, and the Born interpretation says that, well, you have particles who solve wave equations, but if you ask, what do I see in an experiment? If you look for the particle, you will always find it at classical locations, but you will find a distribution of these classical locations that will, if you do really many experiments, will form the same pattern as the wave does. That's the probabilistic interpretation of quantum mechanics. Now, quantum mechanics has been a huge victory, starting from atomic physics and looking outwards to chemistry, molecules. Bohr already looked at molecules. You solve the wave equations for the atomic nuclei, for the electrons in the molecules. You can go into the solids. You solve the wave equation for the electrons in the solids to account for the behavior of conductors, semiconductors, heat conduction, and whatnot. So it's really a big success. And you can go the other way. Inside the atomic nucleus, you have protons and neutrons. They solve Schrödinger equations, adapted, of course, to that situation, and even down in particle physics. It's the same fundamental type of equations we are solving, adding relativity, adding particle components and whatnot. But the quantum program has been absolutely fantastic for science. It has also been fantastic for technology, because all these systems actually have applications in technology. So, of course, we have a chemical industry, we have nuclear power, we have material research, and our deep down understanding of all of this is based on the quantum theory. I'm modest enough as a scientist to know that clever engineers have always been able to build things without having a quantum mechanics textbook on their table. I also have a famous colleague in laser science. He worked with one of the laser companies, and he knew everything about lasers, but he admitted that the engineer could take things down from the shelves faster and build a big, good laser than he could calculate one. So of course, things are happening with and without the participation of scientists. But it's fair to say that, of course, we as the scientists, we know how these technologies work, and more we are now part of the, say, material development in all these sectors. Simulations pave the way for testing many materials, for example. And then there's, just to mention it because it's on the agenda today, of course, all these technologies are also super important in the green technologies. So we will have power to X, we'll have catalysts, we have batteries, we have all these things where chemistry and physics goes hand in hand. And there's a big hope that we can also contribute to this. As I could have made the slide on pharma or defense or IT, because there are so many areas of society where we rely on developing our technologies, and now, again, more and more being guided by simulations and understanding of what's actually happening. So all of this is a fantastic success story. The first quantum revolution is what we sometimes call the mere application of quantum theory to understand the behavior of our technologies. But then the quantum information technology, that's a slightly different story. So that's a long and winding road. This is a beautiful road in Norway. And I think it's still fair to say that the quantum information concept, they take their roots from the very foundations of quantum mechanics. And there were famous discussions between Niels Bohr and Albert Einstein, starting already when quantum mechanics was invented. And you may have heard about them, philosophical discussion, what does it all mean? And these guys never agreed on what quantum mechanics really means. Einstein, he died in 1955, but Bohr kept discussing with him even after he was dead. And of course, it makes it a little bit easier. But what were they discussing? Well, they were discussing this uncertainty and randomness when you do measurement. Where does that come from? And is it really like that? The particle and the wave as coexisting object. What is actually the physical meaning of the wave description? And this collapse of the wave function, as it's called, when you do a measurement and you suddenly see a particle in a particular point, is that really happening in the physical world, as Einstein would prefer, or is it just something that happens in our description of the system, our mental knowledge or picture of what's going on, as Bohr would like it? Very exciting and very, very important ingredients in the next steps. And I just take you on a small detour. Many scientists have been engaged in this discussion until this very day, and many scientists have despised that discussion. We have been there, we have done that. Stop, shut up and calculate. Use the theory for something instead of doing this eternal discussion. What are the foundations? What does it mean? But then I'd like to just remind to you that it is actually that led into a lot of the quantum information concept. Because it was the speculations about these things that started new ideas of what physics can do for us. And it was very scattered theory work, but then I put the subtitle LSD, and that's literally LSD I'm talking about, and CIA, and it's really CIA I'm talking about, because in America there were hippies in the late 60s, early 70s. Of course, we know there was hippies in America in the late 60s, early 70s, but there were also hippies interested in quantum physics. And I can recommend this fantastic book by David Kaiser, historian at MIT, How the Hippies Saved Physics. This is the concept of business casual at the conferences held in California in the early 70s. Literally, people were sitting in these ponds naked and discussing teleportation and quantum and that kind of stuff. And it's also pretty obvious that many of the scientists who were associated with that got a really bad reputation. Okay, but one of them just got the Nobel Prize in Physics last year, Klaus. And he had big difficulties in getting a job, actually, after that. And another one, Alain Aspect, was not attending these conferences, but he was listening to what they were talking about, and his supervisor attended these conferences. And he wanted to do some experimental tests called the Bell experiments. And John Bell warned Alain Aspect, you shouldn't do this unless you already have a permanent position. Okay? And Alain already had a permanent position thanks to the French recruitment system, so he actually was bold enough to go and do the famous Aspect experiment for which he was given the Nobel Prize in Physics last year. So why? Well, that's because some of these crazy things could actually be subject to measurement, and it's right that particles who are quantum mechanical and are in remote locations have a correlation with each other, which is beyond what we know in the classical world. It is really odd, it is really strange. The hippie freaks were not right, and CIA were not right that their agents could use it for communication without radios. But I mean, it was worth a try. And it's also, we know us today, how actually amazing it is that all these entanglement, as it's called, superposition principles, they look like resources for crazy things. But they're not that crazy, but they're still resources for crazy things. But there are also many restrictions on what we can do with it. And that came into understanding in the 80s and 90s. So from 80s into the 90s, not so much guided by the field of quantum information, but just guided by the experimental progress, experimentalists started to build their own quantum systems. Okay? So instead of just taking an atom and understanding the atom, we start putting particles together, make the potentials we like, study the dynamics we like. And I'm myself from the atomic molecular optical side, so I know how we called the field quantum optics. And quantum optics was coherent excitation of atoms. We were actually driving superposition states, wave functions the way we want them. We could also laser cool the ions and atoms so they were under super good control. We could trap them individually, so we could do experiments with one single particle for the first time in the early 1980s. It was no longer ensemble averages. Now it was a single atom doing things in front of our eyes. I've actually even tried it myself, and it's a little bit of a religious feeling to look at a single ion, have a button in your hand, and then give it a little kick with a laser to see what actually happens. It's actually, yeah, I'm still fascinated by it. I still remember 40 years later that I did that once. Bose-Einstein condensates, non-classical states of light, squeezed light, all these things were developed and nobody called it quantum information. And nobody talked about quantum computers in the 80s, actually. This is Herbert Walter. He was director of the Max Planck Institute for Quantum Optics. And he was once asked, what is actually quantum optics? Because he was doing trapped atoms and ions. There was nothing quantum really in it in the beginning, and there was certainly no optics. But he said, quantum optics, that's what I do. And I actually like that, because quantum optics was exactly defined as being what these people were doing. And it was characterized by engineering and manipulating your own quantum system. Okay, so that was the fun, right? And that's also what attracted me as a student in those years. And then there was a parallel thing on which I'm not the expert, but of course there was growing also studies of mesoscopic effect, mesoscopic scale quantum physics. So this is where superconductors and the use of BCS theory came into components. There were Josephson junctions, there were quantum point contact type physics, quantum Hall effect studies in small systems, squid magnetometers. Actually very parallel to what you see on the left, because it's all very foundational, it's also all very academic, but there are also obvious little applications here and there. And I think the field was being driven the same way on those two sides of the slide, that here are quantum devices we make, and it's super fun. And let's see how much we can actually manipulate them. They are artificial atoms or artificial quantum systems, but some of them may have applications. But nobody really talked about quantum computers until a little bit later. There was, I just show all this grass down here in the bottom of the slide, there was now a new modern grassroots movement of theoretical physicists starting asking practical foundational questions. How much information is in a quantum state? How much can I learn about a quantum state? If I give you a quantum state and I allow you to do something to it and you give it back to me, can I measure what you did? To how reliability can you do that? Russian theorist Holevo was pioneering this field. In the US, Hellstrom was pioneering this, Werner in Germany. So there were singular scientists around, and they're actually part of the culture we're still living from today. And so now I just showed the picture again of Bohr and Einstein. You never know what they're really smoking in these pictures. But what happened was that we gradually learned that some of these issues are related to or point to ways to obtain new quantum data security in what's called quantum cryptography, and also into parallel quantum computing, where your bits are no longer 0 or 1, as in the classical world, but you can have a superposition of two quantum states that are mimicking 0 and 1 at the same time. I'll say a few more words about that. I think that the explosion and actually the invention of the field of quantum computing is at this time. This is Peter Shor, who made, so I will not drop many names in this talk in many years, but here's actually the names and years that I want to drop, that Peter Shor in 1994 made an algorithm for factoring that can work with using the principles of quantum mechanics. And Love Grower in 1997 made a database search algorithm that can work with quantum principles. And that triggered a lot of theorists and experimentalists into thinking, okay, can we build such a thing? And I find the paper by Chirac and Soller, 95, for how to do it with trapped ions, as a pioneering paper. It's a super famous paper, of course, but it also points to inspiration in all other platforms, because this idea of thinking, this is my bit, this is how I manipulate the bit, this is how two bits interact, and this is the way we can do it, either by direct interaction between particles or mediated by some common degree of freedom they're talking to. And that triggered lots and lots of proposals over the years. And I will also mention as a super influential work, Daniel Loos and David DiVincenzo, who proposed how to use spin qubits in solids. And after that, a stream of good proposals with superconductors by Nakamura and Moy, and there are also great works here in Sweden, of course, on the superconducting work. DiVincenzo even made a 5+2 criteria for building a quantum computer. The last two is if you want to also build an internet so you can communicate with other quantum computers. And in Europe and the United States, there were roadmaps established. What do we need to do to actually have this thing coming into real existence? So let me say a little bit about quantum computing. So I showed you already this wave function This is the one that was also on my guitar. This is an electronic wave function who is both to the left and the right of the nucleus at the same time. So with a little slip of imagination, imagine that you had a little abacus here with a quantum bead who could be left or right in the classical world, but in the quantum world it could be both left and right. Of course, this is not how our bits look in our computers, but by showing you that one, you know all the time that this is not what it looks like in the computer. And then we can look at how they actually look like. If such quantum states, superposition states exist, then they represent data in a new way compared to the classical computer. And if you have 2 bits, then of course you have 4 different product states, 0, 0, up to 1, 1. So here you have 4 classical data sets represented at the same time in a superposition state. So this is from my high school talk, where I go slowly, and then I say if you have 10, now the kids start looking out of the window, but if you have 10, it's 1024 calculations at the same time. What is striking is, of course, this exponential growth. So if you have 100 bits, okay, that's not a lot. I mean, you have 1 billion in the chip in your smartphone. Here I have 100 bit. Let's say that I can do 1 calculation per second on these very slow and very few bits. That gives me a 30-digit number of calculations per second. And the world's largest supercomputer in Tennessee in America does an 18-digit number of calculations per second. So 100 bits, 1 operation per second, is actually 10,000 billion times faster than the world's largest classical computer. Okay, so this is the promise of quantum, and it's because it does everything at the same time, because superposition states populate all the data states at the same time. So this is what we're dreaming about. We don't harvest that. That's why the Shor algorithm and Grover algorithm are so important, because this being everything at the same time, that's super fun during calculation, but in the end, when you read it out, you're going to read out random numbers, because quantum measurement processes reduce everything to classical. So if you think that, wow, why don't we already have it? It's amazing. It's part of the reason is actually that you can't just throw many, many problems at the computer, because you don't get the many outputs. You get 1 output out of many. And what Shor and Grover showed was that you can actually get the output you want. You can get the factor in the big number. You can get the right element in the database by looking through all candidates, but you actually only want 1 answer in those cases. So this is what we are thinking about. Just a little bit about the physical implementation. So the quantum computer has to do something, and in classical computing, it's very easy, because classical computing is based on bits, and there's a set of universal gates. If you can take any bit and either do nothing or flip it, and if you can take any pair of bits and do the equivalent to what a transistor does, doing a joint operation that depends on 2 bits, then you can do everything. You just have to concatenate these operations over all your bits many, many times. So in the quantum computers, it's actually the same paradigm. So I want to have an operation where my quantum system allows me to do, for example, nothing. That's typically not so hard, but also to do maybe the not operation. And the not means if you are 0, you go to 1, and if you're 1, you go to 0. But it's very important that you don't look at it, because you're not going to first force it to randomly choose between 0 and 1 and then take the other value. You want, if it's 0 and 1 at the same time, you want afterwards that it's 1 and 0 at the same time, because that's what not does on the quantum state. So if you look at it, please don't, because then it will collapse. But if you look at it, you should be careful. But I mean, here's a trick in PowerPoint. So you can see here I actually was able to switch the left part to the right part and the right part to the left. So this kind of coherent physical operation. And if it was a spin particle, who is in a superposition of spin up and spin down, meaning 0 and 1, then rotating the spin by 180 degrees is actually that operation. And that's what you do with a magnetic field. So physicists just have to think a little bit carefully, what is the system and how do I do these operations? 2-bit operations, that's harder. I cannot even do it in PowerPoint, because if this one is 0, I should do nothing to the target, as we call it, but if this one is 1, I should rotate the target. And even PowerPoint cannot both rotate and not rotate something on the screen. But microscopic physical systems can, of course, interact with each other, and in that way mediate this kind of conditional dynamics. And this is exactly what happens by creative people, hence the figure from the Donald Duck cartoons. So you use the atomic system, or you use the solid state equivalent system. So in the atomic world, we have now trapped ions. Every blue dot here is a single trapped ion. There's on the surface, floating above the surface of this chip, who controls the potential for these guys, even controls the operations. And every single ion can be manipulated. That's the NOT operation. But they also interact with each other via Coulomb forces, and that mediates the controlled NOT operation. And here's a a group. You can guess from this picture where it comes from. It's of course a Paris group, so this is the Eiffel Tower. When they do the computations, they actually lay out these individual atoms in a nice 2D grid, and then they do calculations on these systems using similar forces. And optical photons can also be sent into integrated photonic circuits and do equivalent to gate operations. So there's a lot of things going on. In the electronic world, we have superconducting devices. They can also encode qubits. I list here lots of companies and states who are working on that. It's great here in Sweden also. This is IBM and Google who have made these beautiful chips that hold, well, today IBM is above 400 bits, and it's very interesting and very exciting what is happening. Now, finally, a little bit on the historic perspective, except it was all a little bit historical. But I like to make some comments about maybe the difference between Europe and the rest of the world. So through the early 2000s, most research was, in the beginning at least, done in I would say, in Europe and the United States. There were quite similar national and over-national programs, also because the scientists, both here and in the States, were telling the politicians, they do it first. So that's what our American colleagues told the Congress, and that's what we told the European Union. And then in fear of missing out, of course, there were these initiatives made, and that was fine, actually, very good. There was a striking difference that the Americans, North America, Canada included, were actually very fast also having industry on board. And there were, of course, the Google and IBM D-Wave in Canada. And I think that reflects many differences. It reflects that there was a big industry in America who had made tons of money on IT and were willing and capable of going into this business. And we don't have that same big IT industry in Europe. But there's probably a little bit more also a kind of entrepreneurial spirit in America where there's a little bit more, let's wait and see in Europe. And I do remember when the first flagship programs were announced, there was a fantastic official from EU, Pier Paolo Malinverni, and he announced now it all has to go into these big flagship programs. And we all looked scared because we just like our little niche and our little lab and our little research project. And he was smart. He said, I can see you're not all looking happy, but some of you will be happy to run these projects. And of course he was right. There were some of us, not me, who were good at running these projects. And it was actually a very, very good thing that we got these big projects and a lot of science was done. And now it's really coming along. I mean, a little bit late on the hardware side, but the European Union has announced they want 6 quantum computers established near high-performance computing centers in Europe. So this is very exciting, and there's also going to be a project with 2 quantum simulators, each controlling 100 plus quantum bits in near connection to these high-performance computing centers. So this is maybe a little bit late, but I mean, what did we miss at the end of the day? I'm sure we're actually going to be on a good path in Europe. And I have to show you this slide, and then I will finish. At least I try to get eye contact with Anton to see if my time is completely up. These numbers are a little bit random numbers. I want you to look at the $30 billion yearly spending. This is by adding these reported numbers according to which the United States contributes only $1 billion. And of course, there's much more money than $1 billion in America. This is just the single national quantum initiative in America. And the Danish money is also less than we get in money. It's probably even less than is given out by the Novo Foundation. So at some point, take these with a grain of salt. But there's one number I want you to see, and that is that China spends half. So China is, of course, also now a superpower with fantastic science, actually, and really, really good progress being made in this. But it's a very interesting landscape we have now. And now it's no longer Europe and America. Now it's Europe, America, and Asia, of course, which are working on these things. And then we can have a discussion about the Deep South and how to get it global so everybody has access to this. Super. No, I don't want to show you that unless you ask later. So thank you for your attention.
Thank you very much, Klaus. We have a few minutes for questions. If there is anyone who wants to ask Klaus something. Yes.
Since you had the slide ready, I would like to ask about how do you see the path towards
applying? So the next slide, the ones that I apologize to everybody in the room that I couldn't control. Okay, no, so it was actually not about a slide about quantum computing. It's all the other technologies I didn't talk about. There is quantum cryptography. It already exists. It was actually proposed already mid-80s, and there's been experiments since the mid-80s on that. What I had on the last slide was an anecdote I like to tell. The first, here on the left, please go back once, the click mouse. Yes, thank you, that's fine. Or maybe I just control it myself. Yeah, so here is the first transistor, 1947. This lady, it's a picture from 1952. And the story here, the beautiful story, is that the transistor changed the life of millions of people to the better in few years. But she has only one single transistor in that little box. So how does that happen? What is it you can do with one single transistor? And you can guess transistor radio and whatnot. But in fact, it's not. It's a hearing aid. Because a transistor is also an excellent amplifier, low energy consumption amplifier. So all these quantum technologies, one person's computer is another person's sensor. And it's easier to build sensors with few bits than building computers with thousands of bits. And there are many, many proposals around for how we can use the atoms. The atoms are already atomic clocks. They're already gravitation sensors. So this is a parallel effort, which I think has a good focus in Europe. I mean, there's part of the flagship, it's part of specific calls, and I think we all have great hopes for that. I mean, I would be extremely happy if I could make an invention which is just 1% as important, just 1 per mil as important as the hearing aids, because that's a fantastic story.
Right. One last question.
Just a reflection on the difference between America and Europe, that of course the industries, but I mean, in particular, John Martinez, he had a fantastic setup, and that was bought by Google, more or less, right? Yes. The whole group was taken over. So Google had nothing of this before, so they simply adopted it. Yes. IBM had their own, of course. So there are differences, but in Europe, there was no industry even interested in doing anything like that, and that's the problem.
Yes, you're exactly right, and our French at Saclay, there's a group doing this superconducting work, as you know, of course, also very well, and they had a visit from Google, and they say, why is it all in America? But then the guy from Google also said, because you don't have a European industry who can afford it to the same extent. So it's really an interesting story, yes.
Let's thank Klaus again.